I'm Dr. Tim Cooper from the University of the Fraser Valley's Physics Department. It's a pleasure to be here in chillTV, sharing some of the knowledge that I've picked up over the years. 17 years ago, I was a nuclear physicist doing research in nuclear physics. That had been my career. And I realized at that point that there was no point publishing papers to be read in the future if there was no one in the future really around to read them. So I switched from doing research in nuclear physics to giving presentations on climate change. This is approximately my number 190 of the presentations, and it's a pleasure to be here. So I'm going to be talking about climate change or global warming. I use the words almost interchangeably. And without further ado, let's get started on that. Whenever we talk about climate change or global warming, there are four areas that have to be discussed because there's four areas that are important. The first area is the science, and if you can see from the background slide, I put a happy face next to the science because the science is very well understood. It has in fact been well understood for many, many years. We know what the problem is. We also can solve that problem using technology. We have all the technology we need. More would be good, but we actually have everything we need. So I put a happy face next to technology. And how do we have an economic system to bring in that technology? Again, we know how to do that. The economists pretty much agree on how that can be done. But to implement the economic policies to solve this whole problem, we need politicians. And so the last word in my list there is politics, and I put an unhappy face there, because there doesn't seem to be a political solution to this, which is really frustrating. The politicians are getting stories from scientists, but they're also getting stories from many other people. And politicians are unfortunately influenced by people who don't actually have a good grip on what's going on, as is the general public. There's a famous effect in sociology called the Dunning-Kruger effect. The less competent a person is at something, the smarter they think they are. And unfortunately, there are so many experts, so to speak, on climate change telling you things that just aren't so. You'll notice during my presentation, I keep flicking to the left occasionally. I'll try to not do it too often, but I've got a little prompter over there that reminds me of what to say and when to say it. Now that I'm old, my attention span is getting down to about 30 seconds, so you'll have to bear with me on that one. Okay, so I'm going to talk about the science. That's my happy spot. A very brief summary of climate change is, look at the sun icon, planet is getting warmer. As it's getting warmer, some parts of the Earth's surface, such as Italy, Spain, southern United States, Australia, are turning into deserts, they're drying out. As that water vapor goes up from the deserts, it goes into the air. What goes up must come down, and it comes down as heavy rainfall and floods. It comes down as windstorms. So we're seeing bigger windstorms, especially hurricanes. We're seeing more floods in the world, but we're also seeing more droughts. It's not a contradiction. Water isn't suddenly there or not. It's just moving around. Okay? So let's go and do some of the detail of the science. This is my happy spot because I am a scientist. Okay, we have satellites in Earth orbit that are monitoring the sun, and they can tell us how much energy is coming from the sun into the Earth. We also have satellites monitoring the Earth, and they can tell us how much energy is going out from the Earth. If you subtract those two heat flows, or energy flows, you get how much energy is building up in the Earth, and we call that global warming. So global warming we normally associate with the atmosphere, but actually most of the heat, about 93% of it, is going into the oceans. The oceans can absorb all that heat without heating up very much because they have a big thermal capacity, as we call it. You can put a huge amount of heat in without them getting hot. But we live in the atmosphere. So most of my presentation here today will be about the atmosphere. We'll leave ocean warming for another presentation of another person because the effects on the oceans are quite interesting and somewhat alarming. Well, if you put heat into the ocean, we can obviously measure the amount of heat going into the ocean because all we have to do is measure the ocean's temperature at various depths, and then we know how much heat is in there. This graph shows how the heat content of the oceans has been changing. And of course, if you're adding heat to the oceans, the temperature's going up as well. So there's been no let-up in the amount of heat going into the oceans, despite all the talk that's been going on about climate change for the last few decades. Leaving the oceans for now, here's the average surface temperature of the Earth, both the surface temperature of the oceans and the atmosphere. So this is where we live. And you can see from the graph that it goes back over 120 years, 140 years now. The temperature was going down towards the First World War, then it moved up to the Second World War, flat for a bit until 1975, and then whoosh, it takes off like a rocket. Last year's temperature is not included on that graph. Last year's temperature was setting the record for the hottest year on record, and this year is likely to do the same. So notice, if you will, that the temperature doesn't go up smoothly, it goes bouncy, 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 bouncy. Okay. That's just cycles that are going on. It could be sunspot cycles, it could be La Nina, El Nino cycles, many different things in the ocean and in the atmosphere contribute to the overall global temperature. But global warming is the long-term average trend, not what happens in a given year. So why is the ocean warming? What's happening? Well, now as an old scientist, I'm in my really happy spot because I get to talk about old science. Here's my crude picture of the solar system. Here's the sun emitting energy in the form of light. The sun's surface temperature is very hot. It's 5,500 degrees Celsius. That energy comes across space, lands on the Earth, and it warms the Earth. The Earth, in turn, because it's been warmed, radiates energy into space, and it's radiating energy in the form not of light, because it's not as hot as the sun, but in the form of infrared radiation. You're all familiar with infrared radiation. What you can do is go to your kitchen, put your hand over the stove, not too close, turn on the stove, and in the first few seconds, you can feel the heat radiating. That's infrared radiation. That's what the Earth is emitting to space. Now, if the Earth is emitting to space energy at a rate equal to the rate that the energy is coming into the Earth, then the energy balance of the Earth remains the same, and the temperature of the Earth remains the same. If the Earth gets a little bit hotter, then it's going to radiate more energy to space, cool down a little bit, and so the energy of the Earth is going to be basically stable over many years because of this mechanism. Well, it's possible to actually calculate using physics what the average surface temperature of the Earth should be. This calculation was done many years ago by a guy called Joseph Fourier, well known to any physics or math student, and he calculated that the Earth's surface temperature should be minus 18 degrees Celsius. And as a good scientist, he published his calculations and said, this is what I calculate. But there's something weird going on, because even back then in 1824, he knew that the Earth's average temperature was 14 degrees Celsius. So he didn't know why his calculation was wrong, but he was a good enough scientist to realize that when he does his calculation, it disagrees with the data. There's something wrong with the calculation or something missing in it. So he figured somehow something is stopping the heat from radiating away from the Earth. And that's got to be some gas in the atmosphere. He didn't know what it was. He had no idea. It wasn't, in fact, till later on, a physicist called John Tyndall, back in 1859, who took a long tube and filled it full of gases. He put a source of infrared radiation at one end and an infrared detector at the other. And when he filled it with nitrogen or with oxygen, the infrared radiation went straight through, no problem. He then filled it with carbon dioxide. The detector picked up nothing. The infrared radiation would not go through. Carbon dioxide blocks infrared radiation. He also found water vapor did the same thing, which plays a role in our story of the planet. So it was known back in 1859 that the infrared radiation, which would normally go from the Earth to space, is being blocked in the atmosphere by carbon dioxide. Interestingly enough, 3 years earlier, that result was reaffirmed by Eunice Foote, a physicist in the United States. And you say, well, but how can you reaffirm it 3 years before it's been discovered? And that unfortunately represented the fate of women in science back then, because she came across it first, and she did the correct measurements first, but John Tyndall got the credit. I'm happy to say science is a lot more reasonable in the treatment of women these days. But that was especially bad back then. So let's look at a slightly more advanced picture of the solar system. We put another planet in, Venus, and a couple of moons. Well, the Earth is at 14 degrees Celsius. It's warmer than it would otherwise be, according to Joseph Fourier's calculation, because the atmosphere is stopping the heat from getting out of the Earth, the heat is building up more before the heat can get out. The moon, though, has no atmosphere, and its surface temperature on average is about -18, just as Fourier calculated. So physics is good. Physics works as long as you put everything into it. It's all good. Venus's moon is closer to the sun. So for a given square meter of that moon's surface, it's picking up more energy. And so Venus's moon is going to be hotter. And Venus's moon at 7 degrees Celsius makes perfect sense. Venus, on the other hand, as a planet, is 460 degrees Celsius. Ooh, that's hot. That's hot enough to melt lead. Your stove at home doesn't go that hot. So it's a really hot place. And the reason for that is because Venus's atmosphere is huge, thick, and almost completely carbon dioxide. Folks will tell you that don't worry about carbon dioxide. After you've got a certain amount, having a bit more makes no difference. And to those folks, there's a one-word answer: Venus. When I'm giving this presentation in high schools, I then ask the students to see how well educated they are. And I say, hey guys, Venus's moon, what's it called? And I get all sorts of answers. And I get a really annoyed look from them when I say, Venus has no moon. Like those high school kids, I suspect you believed Venus had a moon because I was talking about it, and I'm wearing a tie and a jacket, and I've got a doctorate somewhere. So yeah, it's so easy to deceive people, and unfortunately that's been going on a lot in discussing what's happening in the climate. I promise you in this presentation to be as accurate as possible. I will not try to deceive you in any way, shape, or form. So yes, Venus has no moon. Okay, so a bit later on, people were saying, okay, but carbon dioxide is going up in the Earth's atmosphere because we're burning fossil fuels that caused it to go up. How hot's it going to get? There was a Swedish chemist called Sven Arrhenius, who back in 1896 figured that, well, that would be a good thing because he was Swedish and it was pretty cold in Sweden. So he said, if we double the amount of carbon dioxide in the Earth's atmosphere, how hot is it going to get? And he spent 2 years in his basement doing calculations. His wife and daughter had left him. He was miserable. He had nothing else to do. 2 years in his basement calculating. And he figured that at the end of that, the Earth's temperature would go up 5 or 6 degrees Celsius if we doubled the carbon dioxide content of the Earth's atmosphere, which, by the way, we're in the process of now doing. Well, the interesting thing is that here we are many years later where we have fantastic groups of physicists working on supercomputers, on massive climate models, basically find the same result. And that's because ever since we've been looking at the universe, the laws of physics that it obeys have not changed. So you do a calculation, you get an answer. It doesn't matter when you do the calculation. So in that sense, the science has been understood for 125 years. So it's not new. Well, what has been happening in terms of the data, I have a picture coming up which says, here's how the carbon dioxide content of this atmosphere has changed. Over the last 1,000 years, it's been very flat for a long, long time. We then started burning coal in about the 1900s. That gave off some carbon dioxide, then oil, then natural gas. All of these gave off more carbon dioxide. And carbon dioxide has leapt from 280 parts per million for the last 1,000 years up to about 420 parts per million, which is where it is today. Well, you can see from the picture that at the same time as carbon dioxide going up, so has the heat gone up. So has the temperature gone up. And the temperature goes up slightly after the carbon dioxide goes up because there's a little bit of a lag, as you'd expect. It's like turning on a heater, you don't get immediately hot. So that's our situation. And of course, the key thing of interest is how hot is it going to get? Arrhenius has given us the rough picture. What if we double carbon dioxide? But what if we don't double it? How does the temperature depend upon the amount of carbon dioxide we have in the air? But meanwhile, when I first started giving presentations, over half the population that I spoke to said, well, the carbon dioxide's a natural thing. There's no way you can connect that with burning fossil fuels. But I think most people now accept that the burning of fossil fuels is indeed the source of the carbon dioxide. Coal, which is almost purely carbon, when you burn it, you combine it with oxygen, two oxygen atoms, O2, and a carbon atom, C, go together to give you one molecule of carbon dioxide and a certain amount of energy, which is why we do it. That carbon dioxide obviously goes into the atmosphere after the coal is burnt, straight out the chimney. Oil. Oil consists of, for every whole chain of carbon atoms with hydrogen strung along, for every carbon atom, there's two hydrogen atoms in coal. So when you burn, in oil, when you burn oil, you burn the carbon atom to get some carbon dioxide, you burn the hydrogen atoms, and that actually gives you water. You get energy from both. So for the same amount of carbon dioxide produced burning oil, you get 50% more energy than you would with coal. Methane, which we sometimes call natural gas, has a molecule with one carbon atom and four hydrogen atoms. When we burn it, we get a certain amount of carbon dioxide, but we also get the hydrogens burnt to give us some water, and so we get twice as much energy per ton of carbon dioxide produced from methane as we do from coal. That's why some people are thinking maybe we should switch from coal to methane. I will argue, that actually that doesn't help very much. But that's the situation. We know how much coal we've burnt, we know how much oil we've burnt, we know how much methane we've burnt, because the companies keep records, and that pretty well matches what we see for the increase in carbon dioxide in the Earth's atmosphere. So, carbon dioxide going into the Earth's atmosphere, it raises the question of, well, where's it going? Does it stay there? Does it all stay there? And the answer is mercifully not. Human activity is putting about 11 gigatons of carbon into the Earth's atmosphere. That's the tons of the carbon atoms themselves, not carbon dioxide. One of the problems looking in this area, some people talk about tons of carbon, some people talk about tons of carbon dioxide. The ratio between them, if you've done chemistry, you can work it out, it's 12 to 44. So there's 11 times 44 over 12, or roughly, I think I got that one backwards, 11 times 44 over 12, or roughly 43 gigatons of carbon dioxide is what we're putting into the Earth's atmosphere. But going back to carbon, as it is on the slide, we are putting 11 gigatons into the air. The oceans are nicely absorbing 2.8 gigatons for us, so we're not seeing the full warming that we're actually producing. In exchange for taking the carbon dioxide into the oceans are slowly turning acidic, which is really bad for sea creatures, and a wonderful documentary by some other speaker, perhaps on ocean acidification, would be a great thing for another time. It's outside of my speciality, I won't talk about it. Land plants are absorbing about 3.3 gigatons. So you've heard people say, hey, plant a tree, no problem. Well, all the Earth's trees and bushes and everything else together can't handle the amount we're putting out into the Earth's atmosphere. They can handle only just a little bit less than a third. So if you do the math about how much we're putting out and how much the oceans and the vegetation can bring in, you find we're building up about 4.89 gigatons a year. Every year. That's the average from 2005 to 2014. Well, year by year, you may say, well, we've understood about global warming for a long, long time, so surely we're reducing the amount of carbon dioxide we put in the air each year. And the answer is, in the graph below, no, we're not. Which year had the highest carbon dioxide emissions? Well, that wasn't last year. Usually I have the answer, it's last year, because it goes up every year. But thanks to COVID, last year wasn't the highest. This year, though, likely will be. So we have a problem, we're making it worse, and we're making it worse at an accelerating rate. So if we want to understand what carbon dioxide will do to the Earth's climate, it's useful to look back in history. If we go back over 500, or actually this one goes back 800 years, 800,000 years, you can see the carbon dioxide levels have gone up and down, up and down, up and down. You could just see on the scale, which is to the right-hand side of the graph, there's a little flat spot for 10,000 years, which is really small on this graph, of about 280 parts per million. That's the amount of carbon dioxide that was in the Earth's atmosphere when my grandparents were around. Before then, about 10,000 years before then, it went down to 180 parts per million. That was the Ice Age. Then we had, going back in time, another interglacial, another Ice Age, and so on. Ice ages come and go like clockwork, and it has to do with the Earth's orbit going from a more circular version to a more elliptical version and back. That's why it's clockwork. This is just astronomy at work, just the laws of physics. So we can understand ice ages versus the interglacials, which we're now living in, and it all makes sense. But of course, that massive spike that we've seen recently in carbon dioxide levels is unprecedented. Humans in their present form, with our present brain capacity, have been around about 200,000 years. So that's sort of in the middle of the second bump going backwards. We've never experienced this before. We have no idea what the effects will be on us. But we can at least get an idea of what the effects would be on the planet by looking more deeply into the fossil record, because 3 million years ago during the Pliocene, we had carbon dioxide levels that were much higher. In particular, they were 400 parts per million. So back then, we know that it was much warmer, 2 to 3 degrees Celsius warmer. We also know that sea level was about 15 to 20 meters higher. So that tells us if we leave our carbon dioxide levels where they are at 420 parts per million, we're going to have a lot of warming, and that's going to cause the seawater to expand, glaciers to melt, sea level rise will happen, and we should get between 15 and 20 meters above sea level. By the way, for my Chilliwack audience, the Chilliwack Cottonwood Mole is about 13 meters above sea level. So that's a little bit disturbing to me. We're so far from the ocean, we tend to forget that the Fraser Valley is flat. And so we will be getting flooded eventually here in Chilliwack. Sorry about that. The other thing that's happening with the increase in the carbon dioxide is in the past, carbon dioxide levels have gone up and gone down fairly slowly. But this last increase is 200 times faster than anything we've ever seen before. Although it takes us a little bit far from where we want to go, there have been 5 major extinction events on the Earth. 4 of them were triggered by carbon dioxide levels going up rapidly, but we are going up 200 times more rapidly than back then. So we're well into the 6th extinction event. The big hope, of course, is that we won't be one of the species that go extinct. So what will the Earth look like in the future? Let's not go so far into the future that everybody that I'm speaking to is dead, including myself. Let's just go a ways into the future. The Tyndall Institute for Climate Research in Britain was actually created by Margaret Thatcher many years ago, and they do research, computer models, everything else to try to look at what the Earth will be under given emissions scenarios. So this picture of the Earth, which looks a bit red, is a prediction that was made back in 2005 for what the Earth's temperature will look like in 2080. If you look at it closely, you can see the land areas have gone up about 6 to 7 degrees Celsius. The oceans have warmed much less. And fair enough, the oceans are very deep and very cold. It takes a lot of heat to warm them. So even though most of the heat's going into the ocean, they still haven't warmed up yet. In the decades following this, they will warm up. But this is the Earth in 2080, predicted assuming that the politicians would do nothing to curb carbon dioxide emissions. Back then, they ran optimistic scenarios where the government took a sensible approach or took a slightly less sensible approach or did what was called business as normal, where they just let the whole thing go. So the prediction was this is what the Earth will look like in 2080. And you add 7 degrees Celsius to a whole bunch of places on the Earth. The southern United States is becoming uninhabitable in certain days in the middle of summer, especially when the humidity is high. Italy and Spain are turning into deserts. There's many, many problems. This would be unfortunate, but speaking as somebody who's over 60, I won't see it. I'm just sorry my kids will. But wait, there's more. Did the politicians do nothing about fossil fuels? Well, it's worse than that. They subsidized the industry to encourage it. So we've emitted far more carbon dioxide that could be conceived of back in 2005. So in actual fact, this scenario is expected by 2060. Now, I know what you're thinking. Say, what, 7 degrees? He's crazy. People are talking of 1.5 degrees. Well, yeah. In this picture, the average surface temperature of the Earth is 2 degrees Celsius because the oceans are very big and they're much cooler, and the land mass isn't that large in area. So this is a picture of the Earth at 2 degrees Celsius, which some politicians find quite acceptable. Okay? So I just don't. Well, I don't want to say that carbon dioxide is the only thing that matters climate, there are other things that affect it. And so here's a short list of some of the things that can affect climate, and I'll speak about some of them. The first one I want to talk about is aerosols. And this aerosol is a picture of this aerosol has been taken from above Mission, looking across at Mount Baker. This is the Fraser Valley. This is our home. Can you see that that aerosol, or smog, is looking white from the top? So that whiteness means sun's rays come down to the earth, they hit that white layer, and they bounce back off to space. So they don't hit the ground, they don't warm us up. So that layer is protecting us from warming because it's reflecting the sun's heat back to space. Well, that's all very good. It's also wrecking the air quality, and it's, amusingly enough, it's connected again with fossil fuel burning. It's the major source of that aerosol, and that aerosol kills something like 7,000 people in Canada a year, which, if you scale for Chilliwack's population, is about 20 people in Chilliwack per year die from the burning of fossil fuels manifested through this smog. Well, worldwide, it's given us about a quarter to a half a degree of cooling, whereas the carbon dioxide has been trapping extra heat and has given us about a 1 degree Celsius amount of warming. So we've done two things with fossil fuels. We've got the smog to cool us, we've got the carbon dioxide to warm us. Now, the interesting thing happens when we decide to finally give up carbon dioxide and emitting, and we have to, because the smogs blow away in a few days, suddenly it gets much hotter in a big jump. At this stage, if I'm talking to young people, I say, look, guys, I'm sorry. You're messed up if you do, and you're messed up if you don't. But you're messed up more if you don't cut the emissions. So that's smogs. The next other topic I want to talk about is methane, also known as natural gas. Now, when you put methane into the air, it doesn't stay there very long. It's got a half-life of about 12 years. That means after 12 years, half of the methane you put up there has gone away. Carbon dioxide, on the other hand, has sort of a half-life of about 2,000 years. So carbon dioxide hangs around for ages. Methane has gone relatively quickly. However, when you burn methane, remember I said you get twice as much energy out of burning methane than you would of burning coal per ton of carbon dioxide. But methane has a dark secret. Methane sounds great, but its dark secret is when you extract it from the ground using fracking, some of it escapes. Well, guess what? A ton of methane will capture 120 times as much heat as a ton of carbon dioxide. So even though only 2.3% escapes, methane from fracking actually causes more warming over a 20-year period than carbon dioxide does, obtained from burning coal. So switching from coal-fired power plants to natural gas power plants, not good, not good. And this is what I meant by a whole bunch of people are saying things that aren't exactly true to get their favorite policies accepted by the politicians. So in this graph, you can see how the methane stays in the atmosphere every 12 years. There's half as much goes away. So that's methane. It's not a solution. It's actually a problem. So, well, up north, and here we are in Canada, it's all up north, you could say, we have lots of ice. And sometimes the ice will melt, especially in springtime, and you have a mixture of ice and water. This is a mixture of ice and water seen directly from the top. We don't normally look at ice and water directly from the top, but this is what it looks like. The water looks black, and that's because water absorbs 90% of the light that shines upon it. The ice and any snow that's on it would look white. So it actually reflects 90% of the sun's rays back to space. If we were to melt the ice, make it water, we change an area from 90% reflecting to 90% absorbing. As soon as we do that, that area gets much hotter. This is called the ice melt feedback. Okay? So we're seeing this a lot in Canada. You may have heard that Canada is warming twice as quickly as the rest of the world, and it's due to this ice melt feedback. Well, here's an example of some of the things that are happening. This is a glacier on the boundary between the US, Alaska in particular, and British Columbia. It's the Riggs Glacier, and this picture was taken in 1941. The ice is very thick, about 70 meters. If you take the same picture from the same vantage point a bit later on, I won't say today because this is getting out of date, you can see that the ice level has significantly dropped. Okay? So if you look at that picture from 1941, this is the picture from today. Big difference. The glaciers melted back. But look, this one has trees all over the place. Let me go back. No trees. Trees. Previously, it was too cold there for trees. Now, because the water is exposed, it's absorbing the sun's rays, warming up. It's making it warm enough for trees. So that's happening all around the world, not just this one glacier, of course. Well, I'm going to show a little animation now of the Earth's polar cap, the ice cap at the North Pole. During the winter, the water freezes and the ice cap grows. And then during the summer, it starts to melt back and it gets smaller and smaller. So every year, the minimum Arctic volume of ice occurs around August, early September. And I'm going to show you an animation of what's been happening to the volume of that ice cap over time. Okay, so that's what's happening to the northern polar cap. I always like to draw straight lines on that graph and try to figure out when exactly the North Pole is going to go totally ice-free at the summer minimum. It's something like 5 to 15 years, but it's a dangerous game trying to guess, and so let's just say hand wave, hand wave, hand wave, something like that. Well, what's happening with all of these things? Let's put together what we've been talking about. We have trouble coming, okay? And here, I want to talk about the carbon dioxide from the ocean's feedback effect. It's another feedback effect like the ice feedback effect, and it's something that we've known for many years. Here's a bottle of Coca-Cola, something that's known to most people. I have a little project for you. It's safe to do this one at home. Well, just barely. You go and buy 2 bottles of Coca-Cola, take them home, take the caps off, put one in the fridge, put one on the kitchen counter, go to bed, get up in the morning. Morning, it's breakfast, Coca-Cola for breakfast. Which one tastes the best? And most people would say, well, the one in the fridge. But that raises the question, why would that be? And the answer is that carbon dioxide, like most other gases, dissolve more readily in cold water than they do in warm water. So if you warm water up, gases like carbon dioxide come out. You see that when you're boiling a saucepan on the stove. You see a whole bunch of little bubbles starting to appear long before it starts to boil. That's not steam, that's nitrogen and oxygen largely coming out of the water. So what happens with the oceans if we warm them up? Here is a graph. Look at the blue curve, please. Blue curve is the Earth's temperature going back 450,000 years. We are at the extreme left-hand side of the diagram, which is called 0 on the temperature. It's actually closer to 14.0, but we don't like the 14s. So we've had a flat temperature for 10,000 years, and then it drops to an ice age about 10,000 years ago. Then it gets warm, drop, warm, drop. Above it, on the same x-axis, same horizontal axis, we have the carbon dioxide content of the Earth's atmosphere. And the two track each other pretty closely. What's happening there is orbital changes lift us from an ice age picture more to an interglacial. The Earth starts to warm up. As the Earth starts to warm up, about 800 years later, the oceans start to warm up. Remember, the oceans are very big. It takes a while before they can change their temperature. And as the oceans warm up, so carbon dioxide comes out of the oceans. So you could see, if you're looking at the left-hand side of that picture, that after the blue curve starts to go up on the far left-hand side, the green curve goes up. And there's been an 800-year lag. But then that carbon dioxide that's coming out of the oceans starts to trap heat, even more heat. And so that heats the oceans more. And so the blue curve goes up, but that heats the oceans more. More carbon dioxide comes out, the green curve goes up. This is a feedback effect. Between the interglacials and ice ages on the Earth, there's about an 8 degrees Celsius difference from the top to the bottom. And you can read that from the scale of the graph. But if we didn't have this carbon dioxide feedback effect, it would only be about a 1 degree Celsius swing that comes from astronomy. So it's a big enhancement of that temperature swing. So what are we doing now? We're warming the oceans beyond what they've been ever before. Now, right now, because there's so much carbon dioxide in the air, it's pushing its way into the ocean. But if we start to remove carbon dioxide from the Earth's atmosphere, as we must, a whole bunch of carbon dioxide that we've been storing in there for over 100 years is going to start to come back. So it's going to make life very difficult to lower the carbon dioxide levels of the Earth's atmosphere. That's kind of bad news, but it's still doable. For those of you who are interested in the details of the Ice Age, I've got a little graph here showing the temperature of the Earth for the last 10,000 years. And we're starting on the left. That would be about 10,000 years ago. You can see the temperature goes up, then it's flat for a bit, and then it's been slowly going down, and suddenly right at the end with that red piece, whoosh, takes off like a rocket. That whooshed up in temperature is caused by the carbon dioxide that we put in the air. If we humans had not been here to put that carbon dioxide into the air, can you see that the graph has started to go down and down and down? We're heading back to an ice age. If we go back to the last picture, can you see we're like overdue of an ice age? So had we not put the carbon dioxide into the Earth's atmosphere, we'd be about to have an ice age. We'd be going into an ice age. And then we have all sorts of other problems. Is it good to avoid the Ice Age? Yes. Is it good to burn a bit of fossil fuels just to keep us out of the Ice Age? Actually, I think so, yes. But we've really overdone it. We've burnt way too much. Okay, another feedback to worry about could be most described by this particular experiment. Go and buy 2 steaks. Put one of them in the fridge, put one of them on the kitchen counter. Next morning, steak for breakfast. Well, which one tastes better? You know it's the one in the fridge. But why? It has to do with bacteria. Bacteria can reproduce much faster at higher temperatures than at lower temperatures. So on the steak that was outside in the kitchen, the bacteria will be doubling the numbers, doubling, and they'll all be sort of consuming the steak, turning it into toxins. So that's why we have fridges. Well, guess what? The northern latitudes of planet Earth are kind of like a fridge. So in this picture of the tundra, on the permafrost, if you prefer, up north, you can see there's a whole bunch of frozen vegetables, a huge number. As the north warms up, this ice is starting to melt, these vegetables are starting to rot, and in the process of rotting, they give off they give off carbon dioxide or methane, depending on whether they were submerged in water or not. And either way, they give off greenhouse gases. So we're getting a feedback from our permafrost up north melting, so the Earth is going to get warmer and warmer and warmer if this continues to melt. This is often referred to as a carbon bomb because once it starts to go, it's very hard to stop. I'm happy to report that as of this moment, we haven't passed the point of no return. It is melting, but if we really hurry up and reduce our carbon dioxide emissions, we can help it to refreeze. So we haven't committed to it. And that's good because the total amount of carbon that's in the vegetables up there to actually end up in the Earth's atmosphere would triple the amount of carbon dioxide in the Earth's atmosphere and plunge us way, way into hot territory of something like 8 or 9 degrees Celsius, which is the global average. And remember, what does that mean for the land? Because the oceans won't go up much. So there's another situation that we have to think about where vegetables decay, and that's in a normal, healthy forest. In a normal, healthy forest, trees start to grow. As they grow, they absorb carbon dioxide, and that's good. And they grow, and then, in time, the tree dies, whoomp, falls onto the forest floor, and then it rots. And all the carbon that was in the trunk and the branches of the leaves rots back into the atmosphere. So trees can be a very good short-term solution. Plant a tree, it absorbs the carbon dioxide, but long-term, it all comes back. That's not completely true. There's a teeny tiny amount of it gets stored underground through the roots, but it's really small. And because we've warmed the planet, we've dried our forests, and we've warmed our forests. And so if you live in Chilliwack, you are familiar with the idea that we have far worse and more forest fires now. So that's a way that the carbon can come back out of the trees much more quickly before they even decay. So planting trees doesn't do it. Our forests are no longer net sinks of carbon dioxide. Here's a graph showing how much carbon dioxide is absorbed in different years. The graph starts at 1900, and you can see each year we're absorbing carbon dioxide in our forests. In fact, one of our politicians, Stephen Harper, argued with the world and said Canada shouldn't have to reduce our emissions because our forests are absorbing it all. Unfortunately, as the forests warmed, the growing of the trees didn't really speed up, but the rotting of the trees has. So our forests in Canada are now net emitters of carbon dioxide. And that's somewhat disturbing. That's another example of a feedback effect. So we have hot times coming up, all these feedbacks kicking in. Well, I mentioned that the level of floodwater in the Chilliwack Mole was going to be such as it's up to the roof in the Chilliwack Mole. It may actually be higher because I'm taking into account the fact that we've got the Fraser River. We'll be adding to it. But that doesn't matter. The Chilliwack Mole is just a place. And the sea level is not going to come up that fast. We can walk away, build a house, build a mall, whatever, somewhere else. Now, maybe if you own a business in Chilliwack or a house, that doesn't sound like a very nice thing for me to say, but at least you'll be alive. The big problem with climate change has everything to do with food. It's all food. In China, which has a large amount of land that's quite low-lying, which is one of its major food belts, it is predicted that if we allow the Earth's temperature to go up 2 degrees Celsius, food production is going to drop about 35%. India, about 25%. And many other countries will see losses as well. So Australia just announced fairly recently that they're getting a lot less food out of their land than they would have if the temperatures hadn't gone up. So global warming, the primary danger to humans is food, because that's something that's going to affect everybody. Well, does this have to happen? I've painted a rather grim scenario, and the answer is it depends. The temperature of the Earth is determined by our politicians, not so much by physics. Politicians decide how much carbon dioxide we put out there, then the physics takes over and determines what the temperature shall be. And politicians, that's the subject of our next presentation. With that, I will leave you and see you in the next presentation. Bye for now.